In the next section, we'll look at a further restricted model of computation. And intuitively, the motivation for this is if you go back to how we use the NRAMs in our examples, say the p-click algorithm, we guessed the random vertices. And in a way, we imagine we first guess and then we verify. But if you think about it, the verification was actually in the click problem very fast. It only depended on the parameter. And in that case, we could have said that actually only the last few steps need the non-determinism. In this problem, this was a bit of an extreme example. If you think about the circuit satisfiability, by contrast, you have to pick the variables and then still evaluate the entire circuit. That's going to take more time. So you cannot easily push that all the way to the end. And that maybe gives some intuition for the distinction there. And so the model that we'll look at does exactly that. It has to do the non-determinism at the end of the computation. So that's called tail non-determinism. As we discussed, this WP hard complete problem is too hard. So we have to restrict the class a bit to only keep the slightly simpler problems. So an NRAM, as before, kappa restricted NRAM for a problem is tail non-deterministic if these non-deterministic steps occur in the last so and so many steps, depending only on the parameter. That's the important part. So h, again, is an arbitrary function, but it only depends on the input via kappa. Okay? So as before, NRAM, the number of non-deterministic steps is bounded, but it has to be at the end of the computation. And it turns out this is the final answer for our reductions. It gives rise to this complexity class W1. So these are all the parameterized decision problems L kappa that are decided by such a tail non-deterministic kappa restricted NRAM. It's a bit of a mouthful. And if you wonder what the 1 comes from, that's from an alternative characterization of the same complexity class, where this is a parameter where other numbers can make sense as well. But the point is that this needs a lot of logic and terminology from Boolean circuits and so on that in the end is not used for anything. So instead, I'm using the alternative characterization where only W1 really makes sense. That's the downside. But the definition is more natural. It's just the class that allows such algorithms. Non-determinism bounded by the parameter and only at the end of the computation. Hardness and completeness, just as before. A problem is W1 hard if every problem in W1 can be FPT reduced to it. And completeness adds that it has to be in W1. Now, how can we get to a complete problem this time? And it turns out this is maybe a more natural complete problem than the one before, which is also why we can do the full proof. So that's the problem. It's called the K-step halting problem. Now, people with some theoretical computer science background will remember the halting problem for Turing machines, the infamous problem that is not at all computable, namely deciding whether a Turing machine on a specific input terminates or runs into an infinite loop. That is not possible with any computing device we can think of. And the same is true by reductions about all programming languages that are Turing complete and so on. Now here, we're looking at the halting problem, so there should be some alarm bells in your head ringing. But we restrict the problem so much that it actually becomes solvable. So the input is a Turing machine, an ordinary one, no fancy things, but it is non-deterministic. And it has some input that is also given and this parameter k. And the question is now just, does this Turing machine accept the input? Does it terminate? But after at most k steps. If it keeps running for more than k steps, we're allowed to say no. Okay. And that's, of course, what makes the problem decidable. You can just simulate the machine for a certain number of steps, and then there's two options: it finished or it didn't, right? No infinite loops in the decision, and so that's what makes this problem solvable. So some subtleties about this problem. I guess we would have to somehow specify how we encode a Turing machine as an input to a problem. Remember, it has to be encoded as a language somehow. You can invent various ways to do that, and basically they'll be okay. Both the state space of this Turing machine and the tape alphabet and all components of this Turing machine are now part of the input of our algorithm. So from the perspective of an algorithm that tries to solve the k-step halting problem, it cannot assume that the Turing machine it's going to get is of finite size. Once we have that machine and we start simulating it, it is finite, but we're given the machine itself as part of the input. So that means because the alphabet could be that big, or the number of states could be that big, we can have up to n different non-deterministic choices in each step when we simulate the machine. So what I just sketched, taking that machine and simulating it for a while on a Turing machine, that's already somewhat expensive. It doesn't look like it's in FPT, for example. You would need to spend n to the k plus 1 steps at least, because that's the number of possible non-deterministic paths you have to follow. A side remark is we don't actually need an input here to be given. The problem doesn't change if you assume that there's no input and the machine just has the specific input we're talking about baked in. You could augment the machine so that the first part of its program produces that input, because it's a fixed one, right? We're given the input to the k-step halting problem is a fixed machine and a fixed input, so you might as well combine them. That's a convenient little simplification. Now, the key result that we want to prove is that this problem is indeed a complete problem for our new class W1. And so, yeah, I guess I should stress that the number of steps is the parameter we're looking at. I think I mentioned, but that's important. Okay. Now let's spend a minute to prove this, just because I think it's instructive to see how these things work together. There's two parts, because we're claiming W1 complete. The first part is W1, this is in W1. That's hopefully the easier part. So we have to show that the problem of computing these k-steps can be done with such an NRAM. So the input to the problem is a Turing machine M, an input X, and the parameter K, or the number of steps K. And we'll basically use an NRAM A that simulates that machine. That's relatively easy. We basically follow just the instructions of the Turing machine. Now, I said before, from the perspective of this NRAM, Turing machine can be of unbounded size, and it depends on it's given as part of the input. But that's not a problem, because the NRAM also has the register contents also can depend on the input size. The bigger the input, the larger numbers it can handle. we also have to show that this NRAM is kappa restricted and tail bounded, though. For kappa restricted, how many non-deterministic steps do we need to simulate such a Turing machine? Well, at most k, because we're only simulating it for k steps. And we have some leeway. It could be a function of k in case the simulation is not perfectly getting one random step in the Turing machine simulated with a single step. But certainly we're not running the machine depending on the input size. It's just running depending on the parameter. And tail non-deterministic follows in the same way. We're running the machine for k steps. We might have to do some pre-processing to get the simulation set up. That might depend on the Turing machine size. But then the actual steps only depend on k, how often we have to do it. And copying the output is constant time because it's a decision problem. It's only yes, no. This is in a way same argument, and these can come last. And copying the output is fast as well. Okay, so here that's the trick, that the simulation itself is bounded only by the parameter. That was the first bit. Now we also need to show that it's W1 hard. And for that we need, given some arbitrary problem in W1. That means there is an NRAM for this. Which is kappa restricted, tail non-deterministic, and we have to show that we can solve. Can output the same as this machine A using our problem of simulating k steps of some Turing machine. How are we going to do that? So when you try to simulate A, then A is given some input, some word that could be in the language L. A on Y. Well, the k-step halting problem. K-step halting problem. Let me abbreviate that. So what we construct So we have to give a reduction now that takes this input y So we want to show that L kappa is FPT reducible to our k-step halting problem. So the input to the reduction is y, and what is fixed is a. That's outside of the reduction, right? Because the problem is in W1, we know there is some non-deterministic RAM that decides L. The reduction that we map here, so given this input y that we would feed to a if we were to run that program right away. So we take this y and now we run the machine A for its deterministic part. Deterministic part. And now here comes the magic. The deterministic part can be polynomial in n. No, it can be FPT, but we're doing an FPT reduction. That's fine. So that has FPT running time. But it's deterministic, so there's no choice. It's good enough to run this once at the beginning, and then we take a snapshot of the machine at this point. And basically we encode that. Well, what is the state of the machine at this point? It's the memory contents and maybe an internal state, a program counter, right? So this is memory and register contents. Plus where in the program you are. So we can take that and write that down and construct now a Turing machine that simulates the non-deterministic tail of A. Okay, so that's going to have some slowdown. But again, here the Turing machine, we can give it a number of states that's big enough to represent the number of non-deterministic choices that A is doing, because we're constructing that as part of the input. So I should say it's a non-deterministic Turing machine. And we know that this tail has h of kappa of y many steps. That's from the definition of kappa restricted. There's some function h. So we know for how many steps we will have to run this Turing machine that results from that. If it finishes in that many number of steps, then A would have accepted the input and we can copy the output. Otherwise, we can stop and reject the input. So the output of the reduction now is this Turing machine. The Turing machine and then the number of steps we have to simulate it. And so you can check that this is an FPT reduction. It runs in FPT time because we run A for FPT many steps. We construct something that's I guess the machine A is not even part of the input, it's constant size. And the number of steps is the parameter of the new problem. The number of steps is a function of the parameter of the input. So it's parameter preserving. Okay. And I guess the correctness is almost obvious. The way we construct it, if that machine terminates with that many steps, then A would have accepted input Y and vice versa. So that part here is relatively boring. Maybe we should write down it's an FPT reduction because the reduction takes FPT time. That's from this part up here. That's parameter preserving. That comes from here. And the correctness belongs here as the next component, is essentially by construction. Okay. Not too much time left for nice reductions. But let's zoom out a bit again. So we have the class W1. To remind you, it's the class where you have a tail non-deterministic kappa restricted NRAM that decides the problem. And we found there is indeed somewhat natural complete problem for the class, namely simulating now a standard Turing machine, a non-deterministic one, for a given number of steps, where the number of steps is the parameter. So what can we do from this? We don't usually care about this halting problem. We want to decide more combinatorial optimization problems. And to get to those, we need some intermediate problems to translate away from the machines. And here weighted SAT can be shown to have a variant where this is indeed W1 complete. And so the variant here is, again, the parameter is the weight of the assignment that you have to put, but now satisfiability is a specific normal form for formulas. And in particular here, it's a 2 conjunctive normal form. So it's the same as in 3SAT, but with 2 literals per clause, which is a bit awkward if you remember, because so 3SAT was NP hard. P complete, but 2SAT is in P. But it turns out if you ask for the weighted satisfiability, that is no longer such an easy problem. And indeed, the parameterized problem where you ask for, can you satisfy a formula in 2 conjunctive normal form where the weight has to be exactly K? That turns out to be a W1 complete problem. So which in particular means it's got to be NP hard, right? So to prove this, we have to go, I don't think I've included the proof for this theorem. I'll look into how hard that was. Maybe it led too far. It turns out that this problem still is a bit inconvenient to do reductions from. And you can restrict it a little further, where all the literals are negated. So all the inputs are of this form. You have some not x1 or not x2 and not x3 or not x2 and so on. So all the formulas look like this. It's two things, but you take the negation for all of them. And it turns out that's also W1 complete. And from that, we can do sensible reductions. Okay. So I suppose, again, here going back to the weighted satisfiability needs more logic than algorithms. And so let's not do that. But instead, let's as one final point, at least see one interesting problem that we've started a long time ago with, and see that it's W1 complete. And that's the independent set problem. So parameterized independent set in exactly the same way as we defined it before. The canonical parameterization is the number of elements in the set. As always, the proof has the two parts of in W1 and then the hardness. For in W1, same as for p-click that we've argued before. We use k non-deterministic steps. Of an NRAM. To guess a subset. Of the vertices, and then we use k-squared time to check that there's no edges. So that's kappa restricted because we only do k guessing steps, and it's tail non-deterministic because everything that comes after the guessing is bounded by a function of the parameter only. Okay, so indeed the problem is in W1 because you can solve it with a kappa restricted, tail non-deterministic, NRAM. Good. Interesting bit is the hardness. And for that, of course, we borrow one of the problems that we know to be complete already. So we take the PW-SAT 2CNF minus problem. I know it's lovely to juggle with these names. We prove PW-SAT 2CNF minus can be reduced to our beloved independent set problem. So what do we have to do? We have to construct a reduction, and we have to embed our 2CNF minus formula into somehow a graph. So we're given an instance of this problem, which is some formula. Let me write it like this. There's some variables. Sorry, it's some pairs. Let me maybe comment on this first, because the problem is so restricted. The way a clause looks like is totally specified by two numbers, namely the indices of the variables. Everything else is fixed. It always is negated, and it's always exactly two literals. So the formula always looks like one big AND over some set of pairs, and then each clause is xi negated or xj negated. Okay. And from that, of course, that's one input, and we're also given the weight k, the target weight. And now we have to construct a graph from this. As input to the independent set problem. As vertices, we just take the essentially the variables. And the edge set is the set of all these clauses, if you want. So it's all the combinations where ij is in this set I. When I say you're given the formula, you could essentially just write down this set of pairs, right? That fully specifies the formula. And so we take that formula and we make every clause an edge. If you want to satisfy this formula, you have to make all clauses true. And a clause is true if one of the literals is true, and a literal is true because it's negated if the variable is false. Okay? So setting all the variables to false would make the whole formula true. Seems like an obvious problem. But weighted satisfiability says exactly k variables have to be set to true. In this case, it's important that this is an equal. And so the problem really asks for choosing the right set of variables. And so if I pick an independent set in this graph, I'm picking a set of variables where there's no clause that connects them, which means there's no clause where two variables occur that are both set to true simultaneously. I'm only picking a set of variables, a set of vertices in this graph, where there's no clause that connects them. So all of them only appear in clauses where there's some other variable that I don't set to true. So the clause is still satisfied. Okay. So if G has an independent set of size k, I guess, yeah, I should have said the parameter stays the same. And these variables and no clause contains two true variables. So phi is satisfied. And vice versa, if you have, that's the correctness in one direction. In the other direction, if phi has a satisfying assignment of weight k, then the true variables are an independent set in G. Otherwise, the formula would have a false clause. Okay, so the reduction is actually not super interesting. The tricky bit is how to get to the right weighted satisfiability problem. Okay. We'll look at a few other examples in the tutorials. There's one more reduction that I put on the slides, which is talking about a slightly different problem, which turns out to be a good intermediate problem. That's the partial vertex cover problem. Let's at least briefly introduce it. So as the name suggests, it has to do with vertex cover. But now we're given both a size for the number of vertices, the set of the vertices that's supposed to cover edges. But I'm also giving a threshold for how many edges they need to cover. Previously, that was all edges in the graph. In this problem, you can say it's fine if they only cover 10 edges. So it's a generalization of vertex cover. And remember, vertex cover itself is FPT. So we wouldn't expect it to be a hard problem, a W1 hard problem. But you can show that this partial vertex cover problem is indeed W1 hard. And we can do a reduction from independent set. But I don't know if we have enough time to do that. I could briefly sketch it. Maybe just by picture. So how would we do it? So we're given an input for the independent set problem. It's a graph. And a parameter k, how many vertices we want in the independent set. We keep the same graph. We set t, the number of edges we want to cover, to be k times the number of vertices. So sorry, that's not, we don't keep the graph. That was the other reduction. So we have vertices and edges. The number of edges we want to cover is k times the number of vertices in the input graph. But the new graph consists of the old graph, and then for each vertex we add some vertices wvi, where this ranges from from 1 to the number of vertices minus the degree of that vertex. And the edges are the old edges, and we have to connect these up. So basically create a star. We connect V with its WVIs. Same values for I. So how does that look like in some... that's not what I wanted. Closer from the beginning. Right. Let me just draw the example. So here's our input graph, where we ask for an independent set. Say we want 2 vertices in our independent set, this and this. And that's the largest. And now we fill up in this graph. There's 4 vertices. Every vertex, that's the construction here, gets a number of dependent vertices added in the reduction, which is the number of vertices minus the degree. So this guy has just 1 at the moment, so we fill it up to have degree 4. This one has 2, so we fill it up with 2. This has 2, and this has 3, so it only gets 1. Okay. The choice of our threshold for how many vertices we're supposed to, how many edges we're supposed to cover, is chosen so that we have to cover with every vertex that we pick exactly number of vertices in the original graph, many edges. And you see that this is only possible if you pick what was an independent set in the original graph. If you pick the red vertices, then all the vertices here, the resulting graph is regular. So G prime is size of V regular, which means all the vertices have the same degree. And then the best way to cover edges is if the edges are disjoint. If there's no edge between any 2 red vertices, then every red vertex covers size of the vertex set many new edges, and they don't overlap. And that's exactly the case when the selection was an independent set in the previous graph.